At 15.8, I'm going to go through examples 1 and examples 2. Example 1 asks you to evaluate this, the line integral of the vector field f dot dr over this curve. So it's actually 3 piecewise curves. So you call this C1, C2, and C3. Okay, through this vector field. Okay. So what we have to do, remember what Stokes' theorem says, is the integral of f dotted with dr is equal to the double integral of the curl of f dotted with your ds. So we can either go this route, and in that case we have to find integral of f dotted with dr on C1 plus integral of f dotted with dr on C2 plus integral of f dotted with dr on C3. C1, C2, and C3. So we have to parametrize all of those curves, or we can simply do this. Okay? Calculate the double integral of the curl. So I'm actually going to do both ways. Okay? So for this first one, on C1, I'm going to draw this in the xy plane, just for convenience. In the xy plane, we've got 1, 2, 3, 1, 2, 3. Okay, x and y. We can parametrize this curve. X equals y equals and z equals. So x would be, we're going from here to here. So x would be 3 minus 3t. Y would be 3t and z would be 0. T going from 0 to 1. Notice what I'm doing when t is 0. We're at 3, 0, 0, which is this. And when t is 1, we're going to be at 0, 1, 0, 0, 3, 0, which is right here. Okay. So r of t equals 3 minus 3t, 3t, and 0. R prime of t equals negative 3, 3, and 0. Integral of f dotted with dr is integral f is from up here. F is negative y squared, z, x. Okay, so negative y squared, which is, here's my y. So negative 9t squared, z, which is 0, and then x, 3 minus 3t, dotted with r prime of t, so negative 3, 3, 0, dt. T is going from 0 to 1. So what we get is we're going to do the dot product integral of 27t squared, integral from 0 to 1, and then I get a 0 and a 0. So dt, so I get t cubed over 3, so 9t cubed from 0 to 1, and what I get is 9. Okay, so let's go to the second curve. Second curve is going to be C2 over here, so now I'm going to draw the YZ plane. On the y-axis we're at 3, the z-axis we're at 6, so that's 0, 0, 6, this is 0, 3, 0. I'm going from here to here, so x is going to be equal to 0, y equals 3, minus 3t, z equals 0 plus 6t. Okay, so r prime of t would be equal to dx dt is 0, dy dt is negative 3, dz dt is 6. Okay, so I want the integral from 0 to 1 of f, which again is negative y squared, so negative this thing squared, z, 6t, and x, which is 0. Dotted with r prime of t, 0, negative 3, 6, dt. Okay, so I got this thing, fortunately, times 0 is 0. So what I get is negative 18t dt. I get a 0 there, so 0 to 1. So negative 18 t squared over 2, so negative 9t squared from 0 to 1, so I get negative 9. Okay. Sorry, can you see that? So I just got negative 18t there. And the derivative times 9t squared from 0 to 1 is negative 9. So right now I've got 9 plus negative 9, and then I have to add the integral on the third curve. So the third curve, we're going from 0, 0, 6 to 3, 0, 0. And it's important we're going in this direction. So x is going to be equal to 0 plus 3t. Y is going to be equal to 0. Remember, this right here is the x-axis, and this is the z-axis. And then z is going to be equal to 6 minus 6t. So our prime of t will be equal to 3, 0, negative 6. And I want the integral of f dotted with dr. So the f is negative y squared, so 0. Z, which is 6 minus 6t. And x, which is 3t. And dotting that with our prime of t. 3, 0, negative 6. dt 0 to 1, so I get 0. I've got plus 0, and I've got negative 18t dt from 0 to 1, so negative 9t squared from 0 to 1, I get negative 9. Okay, so adding these three together, I get 9 minus 9 minus 9. I get a total of negative 9. Okay, so let's do it the other way. Now let's do what we could have done over here. So the double integral of the curl of f dotted with your ds. Okay, so f is this thing. So let's find the curl of f, which is I, j, k, d dx, d dy, d dz, negative y squared, z, and x. Okay, so the curl of f is equal to I direction, I've got 0 minus 1. J direction, I've got, I'm going to do this one first, 0 minus 1. The k direction, I've got this minus the y derivative of negative y squared, so that becomes positive 2y. Okay, so if I'm doing the curl of f is equal to negative 1, 2y. Remember when I do this, when z is a function of x and y, I'm going to dot this with opposite dz dx, opposite dz dy, and 1 dy dx. Okay, so I look at my function up here. 2x plus 2y plus z equals 6. My surface is actually z equals 6 minus 2x minus 2y. Right? So I've got negative 1, 2y, dotted with negative dz dx. Well, dz dx is negative 2. The opposite of that is positive 2. Negative dz dy, positive 2. And then a 1. dy dx. Okay. When I do this dot product, that's fairly straightforward. Got negative 2 minus 2 plus 2y. So I've got 2y minus 4 dy dx. When I look at this thing and I project this onto the xy plane, I'm at 1, 2, 3, 1, 2, 3. So y is equal to 3 minus x. So if I do the y's first, y goes from 0 to 3 minus x. And x will go from 0 to 3. Okay, so take the antiderivative with respect to y. So I have y squared minus 4y from 0 to 3 minus x. So I've got 3 minus x squared minus 4 times 3 minus x, and then minus 0. And then I'm going to have to integrate this from 0 to 3 with respect to x, but let's simplify this first. So 9 minus 6x plus x squared minus 12 plus 4x. So I've got x squared minus 2x minus 3 dx from 0 to 3. So antiderivative with respect to x, x cubed over 3 minus 2 minus x squared minus 3x from 0 to 3. So 27 over 3 is 9 minus 9 minus 9, and then minus 0. So I get negative 9. Okay, so this actually ended up being quite a bit easier, but we not only did the problem, we did it two ways. We verified for this instant that Stokes' theorem actually works.